So we finished with torsion of shaft. Next is elastic stability of columns. So you may get 10 or 20 marks questions in this. So it's a part of module 4. So you know what do you mean by column. So in the construction you have seen in many of the construction area where columns or pillar has been built to construct a building or a house, right? So basically a column is a vertical structure. It is subjected to the axial loads. So the other loads are neglected here. So basically a column is subjected with axial load, and we know that any of that member which is vertically placed and the axial load is acting on that member, we call that structure as a column. We call that as a column. So you can see this is one of the example. You have seen many, like this is a pillar that is used in the construction of a building. So here we have different types of column or classification of column. So the first, it is a short column, and another one we call it as a long column. So we define this with respect to a length of the column. So if this is the length of the column and this is when you take a cross section of the column, depending on this length and cross section ratio, we define it as a short column or a long column. That is depending on the ratio of the length of the column to its section, that is a cross section dimension. That is, we can call it as a diameter, length to diameter. That depending on that ratio, we define it as a short column or a long column. So that is if the ratio of this effective length of the column to its lateral dimension, the effective length to its lateral dimension, if it is less than 15, if the ratio of this effective length of the column to lateral dimension is less than 15, we call it as short column. If it is less than 15, that is 15, we call it as short column. If this length of the column to its lateral dimension, if it is greater than 15, then we call it as a long column. So basically these long column fail under buckling load. We tell what is buckling load, and short column it fails under compressions. That is compressive or crushing loads. It fails under crushing. The next definition, just you need to know the definition. Next is radius of gyration, and it is when you consider any of the member if its mass is concentrated. So there is a member, right? So you can see it here. That is, can define this radius of gyration. So with respect to one particular axis, it is the whole mass of this member or area of the body is assumed to be concentrated at a single point. That is, for example, the mass of this member 1, it is M1, for second it is M2, and third it is M3. So these three are at different locations with respect to one fixed point. That is, that point we call it as a radius of gyration, or at this particular point, the mass of all these objects are concentrated at this particular single point. That we call it as a radius of gyration. So it is basically, it is defined as distance from an axis of reference where the whole mass of area of the body is assumed to be concentrated. So we call this as a shortest distance or least radius of gyration. It is which is at a least distance. So that is for mass 1. It is at a distance R1. It is at a least distance. So we call it as least radius of gyration. So just a definition, and also the short and long column is also can be defined with respect to radius of gyration. So that is, if you want to define the short column and long column with respect to radius of gyration. So if the ratio of effective length, it is the length of this member or a column to its least radius of gyration is less than 50. With respect to radius of gyration, if it is less than 50, the length to its radius of gyration, if it is less than 50, that ratio, if it is less than 50, then we call it a short column. If it is more than 50, then we call it as long column. It can also be defined with respect to radius of gyration, the short column and the long column. So next, what do you mean by length of the column? So it is distance from the support. We call it as length of the column. So basically, we take a effective length. So effective length when the column is subjected to force, so it is or a load, it is going to buckle or it is going to bend in that manner where the column is going to bend. So you can see these sketches. So the column is bent from the fixed to fixed point here. So whereas in this sketch also it is going to bend. So whereas in third sketch you can see it is bent, it is straight for a certain portion here, and it is straight for a certain portion. It is bent at certain point for this length. So you can say
ಸಂಬಂಧ ಮಾಡಿದ್ರೆ
the effective length of the column with respect to where the column is bent from initial position. So wherever it is bent to the next bent part, we call that point as the effective length. You can consider this sketch, it is bent from this point to the next point, and you can also see there in the last sketch where it is bent from the initial support to the next point. So that portion we call it as the effective length of the column, or in terms of definition, it can be defined as equivalent. It is the length of the same equivalent column of the same material and cross section area with hinged ends. Hinged ends in the sense it is a support, so that buckling load will be same for both the columns. So that is when compared to the before applying the load, this column initially it was a straighter column. It was a straighter column. So after applying the load, the column is going to bend. The column is going to bend. So the effective length is the one. When compared to length of the column, the length of the column is the one where it is a distance from initial support to next support. Okay. So whereas the effective length is the one where after applying the load, the column is going to bend. So when it is bent, so from the point where the column is bent to the next point, this we call it as the effective length. So whereas in this case, it is bent from the effective length. So whereas in the third sketch, you can see there it is bent at this, and in the last you can also see there. So it is bent from this point to, it is not bent to whole of the portion, it is bent only certain point. This length we call it as the effective length. So just a basic definition. So next is buckling load or crippling load, we call it as. So just a definition for this. So whenever a column is bent, column is applied with a external force or external load, it is going to bend in certain manner such that whenever this load increases, so the column is going to buckle. The buckle in the sense it is going to have a bending moment. So it is going to bend. It is not a straighter beam, whereas it is going to bend in certain manner. When this load goes on increasing at certain point of load, the column will starts to wibble such that it is not stable and the structure can collapse, at that particular point of load where the column is not stable and it is going to collapse. At that load we call it as a load buckling load. So that is a load at which the column is no longer is stable in stable equilibrium condition, and with any further increase in load the column is going to collapse. So that we call it as a buckling load or crippling load. Just the definitions, so it may be asked. So these are the definitions. The last definition, that is slenderness ratio. So with respect to radius of gyration and effective length, the slenderness ratio, it is the ratio of effective length of column to its least radius of gyration. So that is the least distance from the point where all the load is concentrated. So that we call it a slenderness ratio for a column. So here there are different types of supports in the column. So basically we have different types of supports. For all these types, you need to derive the expression that we call it as Euler load or buckling load. Derive the expression for Euler load or buckling load. Definitely you will be having one of the derivation in this. Out of these four, you will be having one. So if you refer any of the paper, old paper, you will be having one of the derivation, that is derivation for buckling load or Euler load, or the types of end condition. Types of end condition may be both ends injured or pinned. So that is just like a simply supported beam what we have studied. Just like that in case of column. So one of the both the ends are with a hinge support. So next is both the ends are fixed. So two of the end of the column is fixed. So next third case, one end is fixed and other is hinged. Last case, one end is free, other end is fixed. So maybe these are those conditions. That is a pinned ends. These are the pinned ends. So you can see that just like simply supported. So it is pinned at both the ends. The what is this column is pinned at both the ends. So next is fixed and free ends. So this is the fixed ends. So here the both the ends is fixed. So whereas this is one end is fixed, other end is free. So here it is fixed at the center and the other end is free. So in this, the last case, one end is pinned, that is hinged, and the other end is fixed. It is completely fixed. So these are the four different conditions. You need to derive the expression for Euler load, or it is called as buckling load. Euler load, expression for Euler load or buckling load for different conditions. So to derive this expression, you need to follow the sign conventions and assumptions. So I'll come to assumption afterwards. So the sign convention is to derive the expression, how to take a positive moment, a bending moment, and negative moment. So this is the initial striker beam, the dotted line shown. It is the AB. AB is the striker column. Striker column. So after applying the load, if the column bends in this manner, that is either in B dash or B double dash manner, so the convexity with respect to the initial striker column, it is the convexity can be seen towards the initial striker column. So if this convexity is seen or if the beam or column is bending in this manner, then we take that as a positive moment, bending moment. So in the second case, if this is the initial striker beam AB, if the beam bends in this manner such that with respect to the initial beam, the concavity is seen with respect to the initial beam like this. So then we take the bending moment negative. So either it can be in the form of C dash or C double dash. In this manner, the column is bending such that the concavity is seen with respect to initial position. Then we take that bending moment as negative. The sign conventions followed to derive the expressions, to derive the expression for Euler or buckling load. Okay. So you need to remember, you need to take this sign convention to derive the equations. So these are the assumptions for any of the derivation which is asked. So with the assumptions, write the assumptions for Euler load and derive the expression for any of the end conditions. So assumption remains the same. So you need to write these assumptions and continue with the derivation. So these are the assumptions made in Euler column theory, or we call it as for buckling load for any of the end conditions. The assumptions in Euler column theory, like the column material is perfectly elastic. So it is a ductile material, elastic in the sense it is a ductile material, homogeneous. So the material properties remains same throughout, and isotropic, right? Isotropic in the sense along the length it is made up of its same material. So it is ductile, it is made up of its same material. Then the second assumption is cross section of the column is uniform. The cross section of the column is uniform throughout its length. So that is, if you take some area of that cross section, it is same along the length of the column. The column is not tapered column, it is a straighter column with uniform cross section. That is the second assumption. Third assumption is the column is initially straight. That is, whatever the column that is considered, it is a straighter column, and the load, what it is applied on the column, it is a truly axial load. What are the other loads? If it is acting, it is very lesser and it will be neglected. Only it is assumed the column is applied with only axial loads and it is derived. The equation is derived. Next, the fourth assumption is the self weight of the column is negligible. So only we consider with respect to the externally applied load, the self-weight of the column is neglected to derive the expression. These are the assumptions made by Euler column theory. Next, the failure of the column is due to a buckling alone. That is, as we defined with buckling. So whenever that load exceeds the limiting value, the column starts to wibble or it starts to buckle. So when it extends, the column collapses. So only the failure of column is due to the buckling. So that is considered. The sixth assumption, the length of column is very large when compared to its lateral dimension. So it is a longer column, that is long column. So the length with respect to its cross section it is very high. Seventh assumption, material of the column obeys the Hooke's law. So it defines with first 2 points. Its stress is proportional to strain for the column under elastic limit. So last assumption. So when compared to bending stress, the direct compressive stress is very small and is neglected. So as it is said with, it is applied with only a axial load, and whatever the compressive stresses that are induced, that is neglected, and the equations are derived. So only it is considered with bending stresses. So these are the assumptions as to be written for any of the four conditions. If it is asked, write the assumptions and derive the Euler load or buckling load for both ends hinged or pinned, both ends fixed. So any of these four. So now let us start with both the ends hinged. So derive the expression for Euler load for a column with both ends hinged or pinned. Okay, so we'll start with this. So any of one derivation you will be getting in the exam, most probably. Okay, you should know the sign convention to derive any of the expression. So let us expression for Euler load or we call it as buckling load. Euler load or buckling load. So it is first case. First case it is both ends pinned. Pinned or we call it as hinged. Pinned or hinged. So here, so let me consider a column. So this the initial column of length, the column AB. Initially, AB is the figure shows a column AB and let the length of the column be, let the length of this column be L. So this theory, what I'm saying, that has to be written by you. Okay. So let AB be the, so this, according to the assumptions has to be written first. So let AB be the long column and the length of this column be L. L. And it is hinged, which is hinged at, it is shown with this, it is hinged at ends A and B. It is hinged at the ends, at both the ends. It is hinged. The support. The support is a hinge support, just like a simply support what we used in beams. It is hinged at end A and B. Or we call it as pinned or hinged. Okay. And let P be the load. Let P be the load acting. Let P be the load, or it is, we call it as buckling load. Let P be the critical load or buckling load which is applied at the end B. Let P be the critical load or buckling load applied at the end B. Due to this applied load, the shaft, the column which is straighter, will change its shape, or it is going to bend. The column is going to bend in this manner due to the applied critical load or buckling load. The column is going to bend with respect to the supports. So the column is going to bend. Column is going to bend as shown. And due to this, so if I take any section, if I consider any section at this, at the column, let me consider any section at the column, that is x such that, so this is the deflection y. The column is deformed or it is deflected by a distance y at the, along the section. So along the section, so this length is the deflection of the column. The column is deflected by a distance y. The column is deflected, so by a distance y, small y. Column is deflected by a distance y. Okay, initially the column was straighter. After applying this load or buckling load or critical load P, it is bent in the form of curved shape. The column is bent in the form of curved shape, and it is deflected with a maximum deflection, that is to a deflection y along the section. Along the section, the deflection of the column is y. Okay. Now let whatever the section consider, the section is, let the section is at a distance x, at a distance x from A. So let this section be at a distance x. So this distance be x, small x. So section what we considered, it is at a distance x from a hinged point A. Let the section be at a distance x from the point A. Okay. Here, what we have considered, it is P. P is a critical load, and X is the distance. X is, sorry, X we have taken. What is this? Y. Y is deflection. Y is deflection. at section, y is the deflection along the section x6. Okay. So now let us find the bending moment. Bending moment at this section x. Okay. Bending moment. Bending moment at this section x. So what we are considered at x6. So what is that moment? Moment at the section xx is, let it be mx, mxx, mxx. So that is equal to, the moment is what? Moment is nothing but force into a distance, force into distance. So here the force acting is P. So the distance with respect to this point it is y. Y is the distance. So and here you need to follow the sign convention. And here also you need to follow the sign convention. What is that sign convention? So if the beam is initially straighter and it bends in this manner, that is convexity is seen with respect to initial beam, then it is positive moment. So if the beam is straighter and it bends so that concavity is seen here with respect to initial straight beam, so then so whether it is a positive moment or a negative moment. So how the beam is bending here? So that it is the initial straight beam. So we can see this concavity with respect to the initial straight beam. So it is bending in this manner, right? It is bending in this manner. So the moment is negative. It is taken as negative, right? So since it is bending like this, since the support is fixed, it is bending in this manner so that with respect to initial strata beam concavity is seen. So that moment is taken as negative. So it is minus. Bending moment at this section it is minus. Moment is load into distance. Load acting is P, distance is Y. So it is P into Y. P into Y. Right? Uh, bending moment along the beam. So that is along any section. It is given by. So just you need to remember this. It is there in deflection of beams. In deflection of beams. So it is given by EI E into Y d square Y by dx square. Mxx is given by EI d square Y by dx square. Just remember this. So you need not write this, just you should be knowing this so that moment can be substituted. So that mxx will be equal to, that is moment along any section. So that is EI. So E is a modulus of elasticity, I is moment of inertia. E is modulus of elasticity, I is moment of inertia for a material. That is with respect to cross section. So E into I d square Y by is equal to to 0. Just rearrange this. I have just rearranged that. Okay. So here, so whatever the you used in mathematics, is as expression is of a general form. This equation is of a general form. So just for your understanding, it is of the form y dash plus alpha square y is equal to 0. It is of the form y double dash. The equation is of the form y double dash. So it is y double dash, it is double differentiation, that is plus alpha square. This is the constant. P by EI is the alpha. The general expression, and the general expression for this, just for your understanding, general expression for this is just a note. And general expression for this equation, above equation, you need to remember that. So I think, yeah, you use this in math. Okay, so now it is right. So general expression for the above equation, it is C1 cos alpha x plus C2 sin alpha x. So it was written wrong. So that you find out the constant C1, C2. So apply these boundary conditions. So at x is equal to 0, so substitute 0, okay, and y is equal to 0 here. So what is that? You will be remaining at y is equal to 0, 0 is equal to 0 is equal to. So when you substitute 0 here, so it is cos 0. This terms becomes cos 0. So when you substitute 0 for this sign, so sin 0 is 0 and cos 0 is 1. So you'll be remaining with C1. So it will be C1 plus 0. Right? So therefore, the constant C1 will be equal to 0. Constant C1 will be equal to 0. So next you apply the second boundary condition at x is equal to L at the point B. At the point B, when you take x is equal to L, so go to second boundary condition at B, x is equal to L, deflection. There is no deflection at this point B, so therefore y is equal to 0. So then substitute here in the equation 1. So here you just have to keep it that in your mind. I am deriving the expression for a Euler load. So Euler load is a critical load. So that load is P. Okay. So when I substitute x is equal to L, so from this, we call this as equation 2. From the equation 2, I know C1 is 0. So therefore, the equation 1 becomes y is equal to 0. 0 is equal to C1 is already 0. It is 0 plus this quantity. 0 plus C2 sin root P by EI into L. X is L. Okay. So here. So so this is C2 sin, therefore C2 sin L into root P by EI will be equal to 0. So by this, C2 cannot be equal to 0. If C2 equal to 0, this whole term will be equal to 0. Therefore, C2 is not equal to 0. So if you just cross multiply that, you will be remaining only with C2 is just a number. When this goes to other end, it will be just a number. So sin L into root of P by EL. This will be equal to 0. So sine of L into root P by will be equal to 0. A sine theta will be equal to 0. So when theta is equal to how much? When this quantity will be equal to, when that quantity will be equal to how much? Whether it is 0 degree or pi, like that, right? So whenever sin theta is 180 degree or it is 0 degrees, so this sin term will become 0. So by taking into that consideration, so will be, therefore, since sin theta is equal to 0 at theta is equal to 0, 5, etc. Therefore, this quantity L into root, therefore L into root of P by EI, when it is equal to 0, 5, etc., this quantity will be equal to 0. So since I want to take a non-zero value, neglect 0, taking non-zero value, L into root of P by EI will be equal to, you can neglect 0 degrees, you can neglect 0, L into root of P by EI will be equal to 5. Or when you just do the squaring on both sides, squaring on both ends, L square into P by EI will be equal to pi square. Okay, just I need to derive the expression for P. So by this above equation I'll be writing here. So when you consider rearrange that, P will be equal to pi square EI divided by L square. So expression for this, the equation 3 is the expression for Euler load or buckling load whenever both the ends are hinged or it is supported. Whenever both the ends are hinged. So you need to remember this equation. Maybe it is that you may be asked with problems or to derive the expression for Euler load or buckling load for the both ends of the column are hinged or pinned. So here you need to remember this. So just remember this expression to derive, and you need to know the sign convention. Just follow the sign convention. So rub this. So with respect to the sign convention, you need to take the moment whether it is positive moment or negative moment. So in the same way, you have another three derivations.